Let's take a closer look at resistance. I have my multimeter here, and these are the probes that are connected, and I have the thing set for on the ohms scale to measure resistance. Right now it's saying 0 with an L, and that means that it's completely disconnected. If I do this, all right, it looks like we have very low resistance, about 0.3 ohms in these leads. If you just touch them gently, it doesn't work very well. You have to really make it firm. Let's go check out this quarter. That's made out of metal. That's low resistance, isn't it? Let's check out the paper. Oh, that's very high resistance. Now we have different scales on here. We can change this to go to measure higher resistances. I'm going to go all the way up to 40 million ohms. Again, this is going to read 0. Now I'm going to check the paper again. Paper is a pretty good insulator. Let's try my hands. Okay, somewhere is around 3 to 4 million ohms between my fingers. Now what would happen if I licked my fingers? Oh, a little bit of saliva with some ions in there, and I'm a better conductor. I'm down to 2 million ohms. Now I've drawn a line on the paper with a pencil, graphite pencil. I'm going to measure the resistance for a short segment. Okay, get about 5 to 6 million ohms. A little longer, I'm at 11 or 10. I go a little longer than that, I'm at 20. This tells me that the resistance increases with length. Resistance is additive in series. What's going to happen if I color the line wider? Now you might think that I'm going to add more resistance because I'm adding more material, which is itself a resistor. Now the long way we were at about 20. Oh, it's a little less now. I'm going to color it in some more. Well, what we've done is we've given the charges more room to move. It's kind of like opening up extra lanes in a traffic jam, and the charges can go through. So what this means is when you're in parallel, these lines are in parallel to each other, the resistance decreases.